Hello everyone, I hope you're well. This set of notes will cover sections 6.1 to 6.6 in the text. We're going to be dealing with chemical reactivity, talking about the characteristics of a chemical reaction in terms of thermodynamics and kinetics. And then the rest of the chapter deals with mechanisms. So the first part of the chapter deals with chemical reactivity, which is where we'll begin. In section 6.1, it deals with enthalpy. And enthalpy is simply the heat energy between the reaction and its surroundings at constant pressure. So enthalpy has units of kilojoules per mole. And it is a form of potential energy. And the change in enthalpy will be the heat absorbed or released from a chemical reaction. So this is a bit of an abstract concept, but we have to remember that it's enthalpy itself. We can think of in terms of potential energy, and it is the energy stored in bonds. It is the energy that is stored in chemical bonds. So when we make and break bonds, sometimes energy is released and sometimes energy is required to do that. So when we get into mechanisms, we're going to be making and breaking chemical bonds. And we have to be able to connect this to enthalpy, or the energy changes associated with that. So breaking bonds always requires energy, and delta H has a positive value. Making bonds always releases energy, which means the change in enthalpy will be negative, and that's considered an exothermic. Change that to exo. That's a typo. I'll fix that later. All right. So when bonds break, they can break in one of two ways. They can break homolytically or heterolytically. Homolytic bond cleavage generates radicals. And notice we have a single-headed arrow. Okay? A double-headed arrow represents the transfer of 2 electrons, where a single-headed arrow transfers 1 electron. So you can see that in our chemical bond, there are 2 electrons being shared. 1 electron goes to the Y atom and 1 electron goes to the X atom to generate radicals. A radical is simply an atom that has a single unshared pair, or a single unshared electron. The other way that bonds can break, and this is going to be the main focus of our mechanisms when we get there, is heterolytic bond cleavage. And that's where a pair of electrons is transferred to one of the atoms. So in the bond, both electrons are transferred, as indicated by the double-headed arrow, to one of the atoms. And bond dissociation energy is simply the delta H value, or the change in heat energy for breaking a bond via homolytic bond cleavage. Now in the text, they have examples with tables of how to calculate this. You will not be required to calculate any bond dissociation energies or use them to calculate delta H for a reaction. Let's focus on exo versus endothermic reactions. Remember, an exothermic reaction is one in which the change in heat is negative, meaning the reaction releases heat to the surroundings. In an endothermic reaction, we have a delta H value which is positive, which means the reaction absorbs heat from its surroundings. So in an exothermic process, we're going to look at the potential energy diagram. We have enthalpy on your y-axis, and you have reaction coordinate or reaction progress on your x-axis. Now there's a couple key points. Now we have our starting materials, which we start here on the left. Notice they have a particular energy. And our products have another potential energy. Remember, this energy, enthalpy, this is the potential energy or the energy stored in the bonds. So if the products have lower energy than the reactants in our exothermic reaction, where did the energy go? It must have been released. That's how we know it's exothermic, when the products are lower in energy. The potential energy gets converted to kinetic energy. And you can think of mathematically, delta H for a reaction is the enthalpy or the change in enthalpy for your products. Let me just simplify this. There's a better way to write it, but let's just keep it simple. Products minus reactants. So if the product, let's make up a number, let's say that's 1, and your reactants or starting materials has a value of 5, we do products 1 minus reactants 5, that's -4. The point is not that you're going to have to calculate this. I want to show you that you get a negative value here. Okay. A couple other points. Let's review the exothermic process. Delta H is negative. The system releases energy to the surroundings. The reactants have more energy than the products. The temperature of the surroundings increases. So if you think about that in terms of, let's just draw a picture. If we have a beaker with some reaction, and the reaction is releasing heat, let's say the reaction is a box, right? We're going to oversimplify that. If the reaction is releasing heat to its surroundings, then the temperature of the surroundings will increase. How would that beaker feel? It would feel like it was getting hotter because the reaction occurring in that beaker is releasing heat. For an endothermic process, let's look at our potential energy diagram. Again, enthalpy on the y-axis, reaction coordinate on the right, on the x-axis. Your starting materials are on the left, products are on the right. Notice that the starting materials have less potential energy than the products. So remember, endothermic reactions require heat. So you must put energy in. Where is that energy going? It's being stored as potential energy. So for this type of reaction, we're converting kinetic energy from the surroundings to potential energy that's stored in the bonds. The system absorbs energy from the surroundings. Products have more energy than the reactants. The temperature of the surroundings decreases, and the products, again, are higher in energy. So one point I'd like to make is what these humps represent. Well, we're going to talk about that later, but that's called your activation energy. Okay. Again, your activation energy goes from the energy of the starting materials to the top of the hump. And up here, this is called your transition state, and we'll talk more about that later. All right, we're going to quickly move through the next couple sections. Entropy is simply a measure of disorder of a system. You can also think of it as sort of dispersion of particles. You can also think of it as the number of states that a molecule's energy can be distributed over. So more disorder means more entropy. Less disorder means less entropy. It's somewhat of an abstract concept. So when delta S has a positive value, that means that the disorder or randomness of the system increases. When delta S is negative, your disorder goes down or the randomness decreases. There are several ways that entropy can change. for physical and chemical processes. Let's look at the ways that entropy, or delta S value, can increase. And by the way, entropy is typically given in units of joules per mole Kelvin. And the ways that it can increase are going from a solid to a liquid, right? So think about that. If your particles are very close together as a solid, and then the particles have much more motion, not that the particles are further apart, but their disorder is increased, and now the particles can slide past each other instead of being locked into place. We have an increase in entropy. Going from a liquid to a gas. This is where we have particles that are close together, that are sliding past each other, can now move into the gas phase where the particles are very far apart. So in both cases, we have an increase in the disorder or dispersion of particles. The next one is the expansion of a gas. So you have gas in a closed container, and then we open that container, and we see that the particles have dispersed. When we increase dispersion or randomness, we increase the degree of entropy, or the change in entropy. When we increase the moles of products, so simple example here, when you go from 1 mole of a product to 2 moles of a product, your change in entropy will be positive. Just like here, change in entropy will be positive. Formation of an acyclic product from a cyclic reactant. So there are less degrees of freedom of motion for a cyclic molecule because it's locked into place. But if you think about this in terms of bond rotation and the possible states that this molecule could occupy in a three-dimensional space, we've increased the number of possible microstates, is what they would call it, for an acyclic molecule. So delta S increases. Section 6.3 we'll move through quickly again. Gibbs free energy. You will not be required to understand, or you will not be required to do any calculations. You just have to have a general understanding of what delta G is. Delta G also has units of kilojoules per mole, and it's the energy associated with the reaction that can be used to do work. So this is the big equation you'll see if you take Chem 4. It's a thermodynamics equation. It's simply a way to repackage entropy. However, you're not going to have to do any calculations with this for this class. What you need to know is that when the value of delta G is negative, that means that it is a spontaneous process in the forward direction for some reaction going A to B. In the forward direction, if it's spontaneous, the value of delta G is negative. This indicates that the reaction is thermodynamically favorable. And we can call that an exergonic reaction, that it's releasing energy. And if delta G happens to be positive, we say that is a non-spontaneous reaction in the forward direction, and it is not thermodynamically favorable. Because this system requires energy, it's endergonic. And we're going to skip the section on equilibrium, but what you need to know from section 6.4 with equilibrium is simply that the delta G value, free energy, is a minimum when a system is at equilibrium, right? As indicated by the double arrow. So delta G is at a minimum whenever a system is at equilibrium. We're going to skip section 6.4. It's mostly just a Chem 1 review of equilibrium. And we're going to move right into kinetics. So let's just review so far what we've learned about reactions. We began talking about enthalpy and free energy, and that is a thermodynamic perspective on why reactions occur. So something occurs if delta G is negative. Those are all thermodynamic characteristics. It's one lens in which we can view a system and try to understand why it happens. But thermodynamics deals with energy. Kinetics deals with speed, or the rate of a reaction. So we're going to take another perspective on a chemical reaction and try to understand it in terms of a kinetic viewpoint. Kinetics is simply the study of reaction rates, or how quickly or slowly a reaction occurs. Reaction rates, the rate of a reaction, has units of the change in molarity over the change in time. So how much of the chemical components are changing in a given amount of time. How much stuff reacts in a given amount of time. The rate of a reaction is always a function of molecular collisions, right? The more collisions that you have, the more successful collisions you have, the faster the reactants will be converted into products. So the number of successful collisions is dependent upon several factors. One, the concentration of reactants. The more stuff you have colliding, the greater the possibility of a successful collision. And the activation energy, right? That's the energy required to get over that hump, right? It's the activation energy barrier. Some reactions need a little push to get going. 3 is temperature. As you increase the temperature, you're going to increase the kinetic energy of the particles. Therefore, you can increase the number of successful collisions as well as the energy of the successful collisions. Geometry and sterics has to do with the orientation of the molecules when they collide, and that helps us to understand if a collision will be successful. And finally, the presence of a catalyst. Catalysts simply speed up reactions. They don't shift the equilibrium, but they make them go faster. And they can do that by actually changing the mechanism by which the reaction occurs. So that was a little bit of background on the factors that affect rate, and we'll talk more about those in a moment. But when we discuss rate, we talk about rate equations, and every reaction has a rate law. And the rate law is simply the rate being the change in molarity over the change in time equals some rate constant times the concentration of your starting materials. Now, the rate depends on these two factors, but the concentration of the starting materials, the dependence upon the concentration of the starting materials can change based on the type of mechanism that's occurring. So to simply understand how concentration affects rate, we can look at the reaction order, which we get by looking at the rate law. So the reaction order, by definition, is the degree to which the reactant concentration can affect the rate. We represent these as exponents, x and y, in our rate equation. The sum of these is called the overall reaction order. So if x equals 1 and y equals 1, then the overall order equals 2. So we said that the rate law helps us to understand how the concentration of the reactants affects the rate. Well, x and y can be all different numbers. Let's say if x is 1, and let's say or other reactant B. So X is 1 and Y is 0. All right. That means that the concentration for this 0, that means the concentration of reactant B does not have an effect on the rate. That the rate is only dependent on the rate of, or the concentration of A. So we say that the reaction is first order. This is your overall reaction order. You take the sum of your exponents. 1 plus 0 equals 1, so it's first order. So if you double the concentration of A, you would end up doubling the rate. For a second order reaction, that could be where A has an exponent of 1 and B has an exponent of 2. This is a second order reaction because if you take the sum of your exponents, 1 plus 1, that equals 2, it's a second order. So what that means is that if the rate of A is doubled, or if the concentration of A is doubled, the rate of the reaction will double. If you double the concentration of B, the rate will also double. Now there's a lot of different combinations of these, but we'll look at one more example, a third order reaction. If the concentration of A, right, if X has an is 2, right, the exponent is 2, and B is 1, so let's look at how the concentrations will affect the rates. Because A has an exponent of 2, if you double the concentration of A, you would end up quadrupling the rate of the reaction. Whereas if you doubled the concentration of B, you would only double the double the rate of the reaction. So concentration affects the rate of a reaction, generally speaking, because when the concentration increases, we have more collisions. However, if we want to understand to a greater degree how concentration affects rate, you need to look at the rate law. And the rate law tells you specifically how the concentration of each reactant will affect the rate of that reaction. All right, let's move to the factors that affect rate. We just talked about concentration, because as we increase the concentration, we have more successful collisions possible that could increase the speed or rate of the reaction. Next is the activation energy. That's simply the energy barrier between the reactants and the products. And if you take your reactant energy, your product energy, okay, so this hump that you see on the potential energy diagram, that EA, that is your activation energy. Now, the smaller the activation energy, or the lower the activation energy, the faster the rate. Let's compare these two graphs. The one on the left, let's call this A and B. Look at the activation energy for A, and then compare it to the activation energy of B. On the potential energy diagram for B, we see it has a much larger EA. That means it's a slower reaction. So the larger, as we increase the activation energy, we decrease the rate. The smaller the activation energy, the faster the rate. You can think of this as going from point A to point B on a bike. And if you have a small hill to get over, you're going to get from point A to point B a lot faster. But if you have a very large hill to pedal up, it's going to take you more time. It's going to require more energy to get from point A to point B. Temperature also affects the rate of a reaction. When you increase the temperature, you increase the average kinetic energy of the molecules. and therefore you increase the number of successful collisions and the energy of those collisions. As you increase the temperature, you increase the number of molecules that possess enough energy to overcome that activation energy barrier. Increasing the temperature does not change the activation energy. Temperature does not change the activation energy. What it changes is the fraction of molecules that have enough energy to get over that hump. So the Boltzmann curve that we're seeing here, you don't have to really worry about this. I don't test you on this. But it just shows you that on the y-axis, we have the number of molecules. X-axis is your energy. At a lower temperature, you can see, let's say that this is your activation energy right here. And look at the fraction of molecules at that lower temperature that have enough energy. The area under the curve can be integrated to give you the sort of the fraction of molecules. So at a lower temperature, we have a particular fraction of molecules that have enough energy to overcome that energy hump. But what happens when we heat the energy? The curve flattens and spreads out, and now we've got a larger fraction of molecules that can overcome that activation energy barrier. So the reaction will occur more quickly. Geometry and sterics simply deals with the geometry of the reactants and the orientation of the collisions. So if the molecule is not colliding with another molecule with the right orientation, then the reaction will not occur, right? If two atoms have to smash into each other and form a bond, then they must collide. Those atoms must collide. But if the atoms don't collide, you can never form a bond between them. So the orientation of the molecule when it smashes into another molecule matters. And finally, the presence of a catalyst. Catalysts simply speed up the reaction rate without being consumed by the reaction. They get recycled and they can be reused for multiple reaction cycles. They do not shift the position of the equilibrium. They simply lower the activation energy, and oftentimes they provide a different reaction pathway for the reaction to occur. So let's look at the potential energy diagram. Without a catalyst, we have one hump in our reaction. That means it's a one-step mechanism. But in our catalyzed reaction, which is in red, you can see that there are 1, 2, 3 humps. That's a 3-step mechanism. So we've changed the mechanism by which the reaction occurs. But in the end, the important thing is that the catalyst lowers the activation energy. The uncatalyzed reaction has a much greater activation energy than the catalyzed reaction. And that's what you need to know about catalysts and their effect on reaction rates. Okay, so in the last section, 6.6, we'll discuss a little bit more on reading these energy diagrams. We want to look at a potential energy diagram from the kinetic viewpoint and the thermodynamic viewpoint. Remember, kinetics is the speed of a reaction. That talks about rate. And thermodynamics is overall energy. So in terms of kinetics, when you're looking at a potential energy diagram, you're going to focus on the activation energy. The lower the activation energy, the faster the rate. So a kinetically favorable reaction is one that has a low activation energy. And in terms of thermodynamics, we're not looking at the activation energy. We care about the change, the overall change in energy. It could be enthalpy, it could be delta G. It really doesn't matter. But it's a change in energy. So the more energy that's released, the more thermodynamically favorable it will be. So the lower the energy of your products, we increase the thermodynamic favorability. So again, to summarize, for kinetics, you look at activation energy. In terms of thermodynamics, you're looking at energy. And the last thing we'll discuss in terms of reading energy diagrams is when we're looking at a diagram, we need to be able to identify a transition state versus an intermediate. A transition state is simply a high energy species. The bonds are in the process of being made or broken, and you cannot isolate this, meaning you can't separate it out through some physical separation method. Intermediates are short lifetime, they're a little bit lower in energy than transition states, and they're not in the process of making or breaking bonds. We can use physical methods to identify intermediates. They're very hard to isolate, but we can actually observe their presence using certain techniques and laboratory methods. All right, so in our first example, we have a three-step reaction as indicated by three humps. So at the top of each hump on your potential energy diagram, those are transition states. And the valleys are your intermediates. So the peaks are transition states, the valleys are intermediates. So typical question, I give you an energy diagram and say how many intermediates are present. If you see two valleys, then you have two intermediates. If I gave you this energy diagram and said how many transition states are present, you would say, oh, there's three peaks. So there's three transition states. And the next potential energy diagram, we have one hump, so that's a single step mechanism. And I just wanted to show you this so you could see that the transition state, sometimes it gets the symbol with a double dagger. And the transition state is a very high energy, right? The energy is the highest. High energy chemical species where bonds are in the process of being made or broken. So where we started with a carbon-bromine bond and we're ending with a carbon-chlorine bond. So this is the point at which the carbon-bromine bond is breaking and the carbon-chlorine bond is simultaneously forming. So it's a very high energy species. You cannot isolate that. And it's where bonds are breaking and forming simultaneously.